morning everybody, welcome back. Today in chemistry we will discuss about vapor pressure of liquid solutions. Yes, up to yesterday class we studied Henry's law, then we are going to discuss vapor pressure of liquid solutions. Okay, first one, what is the definition of vapor pressure? Vapor pressure definition. See, if you take a vessel, I am taking only one liquid, say it is water. For example, it is water. It was closed by taking a lid and it was heated slowly. The temperature rises. Some of the molecules are changes into vapor state. Means the liquid molecules which having more kinetic energy are ready to escape from the surface of solution. So the process of evaporation of liquid molecules into vapors, conversion of liquid into vapors is called evaporation. During evaporation, the level of this liquid decreases. Okay, the vapors come to atmosphere higher place and their temperature is lesser. That's why the molecules, vapor molecules, again on condensation, they becomes to droplets of liquid and again they fall into the liquid. That is called as condensation. During condensation, level of the liquid increases, but yet one stage reaches by continuous heating, the level of the liquid remains same. Why? In that position, the number of molecules which are changes from liquid to vapor is equal to number of molecules that are changes from vapor to liquid. That is called as equilibrium. Which one? Liquid and vapor are in equilibrium. At that position, the vapor molecules exert some pressure on the surface of the liquid. That pressure is called as vapor pressure. What is the definition of vapor pressure? Now I am telling. The pressure exerted by vapors of a liquid on the surface of solution, which is equilibrium with its liquid at a given temperature, is called vapor pressure. Once again, I am telling the definition. Pressure exerted by vapors of a liquid on the surface of solution, which is equilibrium with its liquid at a given temperature, is known as vapor pressure. That is called vapor pressure. Okay, so I am telling the definition. Pressure exerted by vapors of a liquid on the surface of solution, which is equilibrium with its liquid, is called vapor pressure. That is the point. Pressure exerted by vapors of a liquid on the surface of solution, which is equilibrium with its liquid, is called vapor pressure. Right. Now our topic is vapor pressure of liquid-liquid solution. Liquid-liquid solution. Let a solution is prepared by mixing of two volatile liquids. What is the definition of volatile liquids? Generally, liquids are volatile. They are easily changes into vapor state. They are called volatile liquids. This is first liquid A. Like that, I am taking another liquid. This is liquid B. Liquid. I am mixing the two liquids. I am mixing the two liquids into third vessel, into this vessel. This is a solution which contain liquids A and B. It is a solution which contain two liquids A and B. Both are volatile liquids. Volatile liquids. Volatile means they are easily changes into vapor state. Okay, now I am taking this solution. This is our topic now. It was taken, right? This is the surface of the liquid. The surface of the solution contain both liquid A and liquid B molecules. Entire solution, A molecules are there, B molecules are there. A molecule, B molecule. A, B molecules are there. Okay, on heating, these liquids are changes into vapor state. Both liquid A changes into vapor state, liquid B also changes into vapor state. Both are changes into vapor state. So here A vapors are there, B vapors are there. They exert some pressure on the surface. So Raoult, R-A-O-U-L-T-S, Raoult, scientist name. Raoult proposed one formula that is called as Raoult's law. Raoult's law of a liquid-liquid solution. Raoult's law of a liquid solution. What is the statement? According to Raoult's law, the partial vapor pressure of each component over the solution is proportional to mole fraction of the component in the solution. Partial vapor pressure of each component in the solution is directly proportional to mole fraction of the component in the solution. Just like Henry's law statement. So it states that, statement is very important, it states that partial vapor pressure of each component, partial vapor pressure of each component of the solution is directly proportional to its mole fraction in the solution. Its mole fraction in the solution. This is the point, isn't it? Okay. Okay, now apply that one. Suppose here I am preparing a solution by mixing two liquids A and B. So pressure exerted by liquid A over the solution. Pressure exerted by one liquid A over the solution. PA is proportional to XA. What is meant by PA? PA is equal to partial pressure of A over the solution. XA is equal to mole fraction of the A in the solution. By removing proportional constant, so PA is equal to P naught A into XA. PA is equal to P naught A into XA. What is meant by P naught? Vapor pressure of pure A. If only liquid A is present, no B, only liquid A is present. What is the pressure exerted by A? That is called vapor pressure of pure A. Okay, see I am writing here PA is equal to partial pressure of A. Partial pressure of A. P naught A, vapor pressure of pure A. XA is equal to mole fraction of A in the solution. Similarly, PB is proportional to XB. That implies PB is equal to P naught B into XB. PA is equal to P naught A into XA and PB is equal to P naught B into XB. So, two liquids vapor pressure in the mixer. According to Dalton's law, PS is called the total vapor pressure of the solution. According to Dalton's law, PS is equal to PA plus PB. PS is equal to PA plus PB. So here PS is equal to PA means P naught A into XA from this plus PB means P naught B into XB. P naught B into XB. This is a formula for vapor pressure of liquid solution. Vapor pressure of liquid solution. Okay. Now suppose we know XA plus XB is equal to 1. Sum of the mole fractions of all components in a mixer is equal to 1. Therefore, note down all these things by stop that video. PS is equal to P naught A into XA plus P naught B into XB is equal to, we can write 1 minus XA. Right, we can write 1 minus XA. Therefore, that is equal to P naught A into XA plus P naught B minus P naught B into XA. PS is equal to. In these two cases, XA is the common factor. Therefore, PS is equal to P naught B plus P naught A minus P naught B into XA. One more formula for vapor pressure of liquid solution, total vapor pressure. Or we can solve this one as PS is equal to, if you take here P naught A plus now it becomes to P naught B minus P naught A into XB. This is formula 1, formula 2, formula 3. These are all formulas for calculation of vapor pressure of liquid solutions. Vapor pressure of liquid solutions. This concept I am explaining by taking one graph. Okay? Note this one. Right? See, I am drawing a graph between vapor pressure versus mole fraction. Vapor pressure on y-axis, mole fraction. Mole fraction on x-axis. Mole fraction. See, I am taking 10 samples of liquids. 10 samples. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this, only A is present. Mole fraction of A is equal to 1 now. Mole fraction of B is equal to 0. Means only liquid A is there here. Liquid A. In the second case, mole fraction of A is equal to 0.9, mole fraction of B equal to 0.1, and so on. Here, mole fraction of A is equal to 0.1, mole fraction of B is equal to 0.9. And the last case, mole fraction of A equal to 0, mole fraction of B is equal to 1. Like that, I am taking 10 samples. Gradually, I am decreasing number of moles of A decreases and number of moles of B increases. First one, here only A is there. First case. So in that case, the total vapor pressure is due to P naught A. So that's why this point is called as P naught A. It is the vapor pressure of pure A. In that 10 samples from left to right, each sample mole fraction of A gradually decreases. Then the pressure caused by A also decreases. Therefore, the graph is come like this. This graph shows pressure of A. And at the last point, at this point, mole fraction of A is equal to 1, mole fraction of B is equal to 0. And the last point, mole fraction of A is equal to 0, mole fraction of B is equal to 1. And mole fraction of B is equal to 1. Totally, it is called as vapor pressure of pure B. That is known as P naught B. Okay, from that point to here, pressure caused by B gradually increases. And what is this graph? This is pressure caused by B, and this is called PS, which is PA plus PB. Any step, any time, you can find the total pressure. If you want total pressure at this time, for example, I am telling at this time. So here, from this point to here, this is the pressure of A. This point to here, that is pressure of B. PA from this point to here, and PB, this point, if you add this one, will get this is the one total pressure. Right? See, this is PA, and it is a point up to this. This is PB, and this one is called PS is equal to PA plus PB. That is a point. We can find total pressure. This is graphical quotation. Okay, leave this one, not required now. For understanding purpose, I wrote this one. This graph is enough for us. Okay? Note this graph. It is very important one. Right. See, you know, HCA is called mole fraction of A in solution. Mole fraction of A in solution. Remember, this is the solution. And these are the vapors. In vapors also, A and B are present. That very important point. If YA and YB are mole fractions of the A and B in vapor phase, XA and XB are mole fractions of A and B in the solution. In vapor phase, the mole fractions of A and B are YA and YB. Remember, YA and YB are mole fractions of A and B in a vapor phase. Vapor phase. According to Dalton's law, partial pressure of a gas is equal to mole fraction of the gas into total pressure, which was studied in a previous year, last year, state summary chapter. Therefore, in that area, we can write PA is equal to partial pressure of A is equal to YA into PS and PB is equal to YB into PS. This is the points. PA is equal to YA into PS and PB is equal to YB into PS. PA and PB are partial pressures of A and B in the mixer. YA and YB are mole fractions of A and B in vapor phase. PS is the total pressure. Understand? So this is the concept of vapor pressure of liquid solution or vapor pressure of solution containing volatile liquids. Liquids means they are volatile. Volatile means they are easily changes into vapor state. Easily changes into vapor state. Understand? So this is very important. Once again, see what is the definition of PA, PB, XA, XB, P0A, P0B, YA, YB. What are the terms? The terms are very important. PA is equal to partial pressure of A. Note down. PA is equal to partial pressure of A. Okay. PB is equal to partial pressure of B. PB is equal to partial pressure of B. XA is equal to mole fraction of A in solution. That is important. Mole fraction of A in solution. Remember, XB mole fraction of B in solution. Mole fraction of B in solution. P0A vapor pressure of pure A. Vapor pressure of pure A. P0B vapor pressure of pure B. Vapor pressure of pure B. Okay. YA mole fraction of A in vapor phase. Mole fraction of A in vapor phase. Write down. YB mole fraction of B in vapor phase. Mole fraction of B in vapor phase. Okay, it's very very important. Then we'll do one problem on this concept. Okay. Write down one problem. The question is, the vapor pressures of pure liquids A and B are A and B are 450, 450 and 700 millimeters of mercury. Vapor pressures of pure liquids A and B are 450, 700 millimeters of mercury. Mercury respectively at 350 Kelvin. Find out the composition of liquid mixture. Find out the composition of liquid mixture. Liquid mixture. If total vapor pressure is 600 millimeters of mercury. Total vapor pressure is 600 millimeters of mercury. Also find the composition of the vapor phase. Also find the composition in vapor phase. Okay, this is the point. So composition in liquid phase means he is asking XA and XB. Composition of the liquid mixture means he is asking XA and XB. Composition in vapor phase means he is asking YA and YB. YA and YB. Note this problem first. Completed. This is a given problem and he is asking XA, XB, YA, YB. Right. Note down. I am erasing that one. Given data PA is equal to P naught A. P naught A is equal to 450 millimeters of mercury and P naught B is equal to 700 millimeters of mercury. 700 millimeters of mercury. This is the given data. PS is equal to 600 millimeters of mercury. That is. Then he is asking XA, XB, YA, YB. Okay, no problem. According to Rolle's law, liquid solution. According to Rolle's of liquid solution, PS is equal to P naught A plus P naught B minus P naught A into XB. This is formula. From that we can find XB. Right? PS is equal to how much? 600 is equal to P naught A value 450 plus P naught B 700 minus P naught A 450 into XB. So 600 minus 450 is equal to 700 minus 450 how much? 250. 250 into XB. 150 is equal to 250 into XB. 0, 0 cancel. So 5 3 times 5 times. So XB is equal to 3 by 5. Right? XB is equal to 3 by 5. Then XA plus XB is equal to 1. So XA is equal to 1 minus XB. 1 minus 3 by 5. So 5 minus 3 by 5. Nothing but 2 by 5. That is the answer. Right? 2 by 5. It is one question. Note down. Stop the video and note down. Okay, right. XA, XB are completed. Then he is asking YA and YB also. Right. Complete this is. We know PA is equal to YA into PS. PA is equal to YA into PS, right? YA into PS. PA means P naught A into XA is equal to YA into PS. PA equal to P naught A into XA. We know P naught A. P naught A value how much? 450 into XA value 2 by 5 is equal to YA into PS is equal to how much? 600. Right? Simplify that one. 0, 0 cancel. 15 3 times. 15 4 times. 2 times. Then YA is equal to 3 by 10. If YA is equal to 3 by 10, that implies YB is equal to 1 minus YA. 1 minus 3 by 10, 7 by 10. Okay? So these are the compositions of XA, XB, YA, YB. Understand? Note that one. Okay. Write down next question. I am giving homework to you. One question on the same model. Not this question. Question. 100 grams of liquid A in bracket molar mass 140 gram mole inverse. 100 grams of liquid A was dissolved in 1000 grams of liquid B. 1000 grams of liquid B in bracket molar mass is equal to, molar mass is 180 gram mole inverse. The vapor pressure of pure liquid the vapor pressure of pure liquid A, pure liquid B was found to be pure liquid was found to be 500 torr. Calculate the vapor pressure of pure liquid A and its vapor pressure in the solution. Its vapor pressure in the solution. If total vapor pressure of the solution is total vapor pressure of the solution, total vapor pressure of the solution is 475 torr. Same model question. First note down 2.36. Calculate the vapor pressure of pure liquid A and vapor pressure in the solution. Means he is asking P0 TA and PA. Answers are, please try this one. P0 TA 280.7 torr. And that is 32 torr. PA is equal to 32 torr. These two are the answers. Just try. Okay? Right? Go to that one. You solve that one, try that one. Same model. Please solve that one. Next concept, vapor pressure of solid in liquid. Vapor pressure of solid in liquid solution, or that is also vapor pressure of a solution containing non-volatile solute. Vapor pressure of a solution containing non-volatile solute. So subheading is vapor pressure of solid in liquid solution. Solid in liquid solution, or vapor pressure of a solution containing non-volatile solute. Vapor pressure of a solution containing non-volatile solute. This is okay. See, let I am taking water, a pure solvent, in a vessel. This is only solvent. This is H2O, water. Another vessel I am taking. This is 1 small m urea solution. 1 molar urea solution. 1 molar urea means 60 grams of urea dissolved in 1 kg of water. That is called 1 molar urea solution, because the urea molecular weight is 60, isn't it? Okay, now this is 1 molar urea solution. The surface of the solvent contain all are solvent molecules. All these are only solvent molecules. But surface of the solution contain, this is solution, the surface contain both solvent and solute molecules. See, this is a solvent molecule. This is a solute molecule. Solute molecule. Because it is a solution. It is only solvent. Now, my question is, when a non-volatile solute is added to a solvent, we are getting solution. The vapor pressure of solution always less than vapor pressure of pure solvent. Vapor pressure of the solution always less than vapor pressure of pure solvent. Why? That is the point. Vapor pressure of solution always less than vapor pressure of pure solvent. Why? The reason is, listen, very important point. Okay, these are changes into vapor state. So these are all solvent molecules. But here these are only solvent molecules. See one point, in solution and solvent, only solvent molecules exert pressure. Right or wrong? Because solute is non-volatile. Non-volatile means it cannot change into vapor state. Because it is a solid solute. Solid solute, now it is dissolved. It is dissolved completely. Solution is formed. In that solvent is volatile, easily changes into vapor state. But solute is non-volatile. It cannot change into vapor state. So, in pure solvent and solution, only solvent molecules exert pressure. The surface of the solvent contain all are solvent molecules, but surface of the solution contain both solute molecules and solvent molecules. Solute molecules cannot change into vapor state, and they prevent vaporization of solvent molecule which are present below it. Therefore, the rate of evaporation of solvent molecules from the surface of solution is less than pure solvent. Rate of evaporation of solvent molecules from the surface of solution is less than pure solvent. Hence, vapor pressure of solution containing a non-volatile solute is always less than vapor pressure of pure solvent at the same temperature. Vapor pressure of solution containing non-volatile solute is always less than vapor pressure of pure solvent containing non-volatile solute. Contain non-volatile solute. Let P naught be the vapor pressure of pure solvent. This is P naught. P naught. P is equal to pressure of solution. Vapor pressure of solution. Always P less than P naught. True. Always P less than P naught. I told the reason because in P naught and P only solvent molecules except pressure. Okay? Right. The difference between vapor pressure of pure solvent and vapor pressure of solution containing non-volatile solute is called as lowering of vapor pressure. That is called as lowering of vapor pressure. It is one important question. The question is, what is meant by lowering of vapor pressure? What is meant by lowering of vapor pressure? The difference between vapor pressure of pure solvent and vapor pressure of solution containing non-volatile solute is called lowering of vapor pressure. The difference between vapor pressure of pure solvent and vapor pressure of solution containing non-volatile solute is called lowering of vapor pressure. Let P naught be the vapor pressure of pure solvent. P is equal to vapor pressure of solution. Therefore, P naught minus P is equal to lowering of vapor pressure. Which is called as LVP, lowering of vapor pressure. Okay, so this is a very, very important one. Right, if lowering of vapor pressure is compared with vapor pressure of pure solvent, lowering of vapor pressure is compared with vapor pressure of pure solvent, that is known as relative lowering of vapor pressure. If lowering of vapor pressure is compared with vapor pressure of pure solvent, it is called relative lowering of vapor pressure. That is called relative lowering of vapor pressure. So that is P naught minus P by P naught. P naught minus P by P naught is called RLVP. This is the one. Relative lowering of vapor pressure. P naught minus P by P naught is called relative lowering of vapor pressure. Understand? So this is the concept. So tomorrow class will continue. Okay? Thank you.